March 19, 1945, 50 miles off the coast of Japan, Lieutenant Commander Joseph O'Callaghan gripped the steel railing as USS Franklin shuddered beneath another explosion, the 23rd in less than an hour. Through the choking black smoke that poured from every hatch and doorway, he watched sailors aim fog nozzles into the inferno that had consumed the hangar deck. 3 years earlier, naval officers would have laughed at the idea of using what looked like garden sprayers to fight a fuel fire aboard an aircraft carrier. Today, those same fog nozzles were the only thing standing between 700 men and certain death. The story of how a rejected idea from a New York City firefighter became standard equipment on every warship in the United States Navy is one of the most remarkable transformations in military history. It began not with admirals or engineers, but with men who fought fires in tenement buildings and dockside warehouses, men who understood that sometimes the smallest droplets of water could accomplish what torrents could not. What none of them knew in those early days was that their persistence in the face of institutional rejection would reshape naval warfare itself, saving not just hundreds of ships, but tens of thousands of lives, and creating firefighting doctrine that would endure for more than half a century. To understand how this transformation occurred, we must return to the crisis that began 4 years earlier on a Sunday morning that would change everything the Navy thought it knew about fighting fires at sea. When Japanese aircraft struck Pearl Harbor on December 7, 1941, they ignited fires that revealed a terrible truth about American naval preparedness. The scale of the disaster was unprecedented. In less than 2 hours, the Pacific Fleet suffered catastrophic losses that would reshape American naval doctrine for generations. The battleship Arizona exploded and sank in 9 minutes, her forward magazine detonating with such force that the blast wave shattered windows miles away and was felt across Oahu. The explosion lifted the 33,000-ton vessel partially out of the water before she settled back and began her final plunge. More than 1,177 men died, most of them trapped below decks as fire and flooding overwhelmed damage control parties who lacked the tools and training to save their ship. The forward magazine explosion was so powerful that it broke the ship's back, sending the bow section plunging to the harbor bottom, while fires consumed everything after the break. Oklahoma capsized in 12 minutes, rolling slowly to port as torpedo after torpedo struck her hull. 429 men were trapped inside as the battleship turned turtle, her bottom exposed to the sky, while hundreds of sailors pounded desperately on the hull from within. Rescue parties could hear them for days, cutting through steel with acetylene torches in a frantic race against time, asphyxiation, and rising water inside the inverted compartments. Some men were saved, but most perished in the darkness. West Virginia settled into the harbor mud, her decks ablaze with burning oil that had spilled from ruptured fuel tanks. The fires burned for approximately 30 hours, fed by oil floating on the water's surface and petroleum vapors rising from damaged tanks throughout the ship. Firefighting teams fought desperately to contain the flames, but lacked the equipment and techniques needed to extinguish fires burning on water or cool superheated spaces filled with petroleum vapor. The ship slowly settled over 3 days as flooding spread through compartments damaged by torpedoes and bombs, eventually coming to rest on the bottom with only her superstructure visible above water. 106 men were killed. California burned as she slowly sank over a 3-day period, fires raging through her superstructure while water rose steadily through her lower compartments. 2 torpedoes and a bomb had opened her hull to the sea, but it was fire as much as flooding that doomed her. 104 men were killed and 61 wounded as firefighting teams struggled unsuccessfully to contain both elements. The ship finally settled to the bottom with her decks awash, another victim of inadequate firefighting capability. Nevada became the only battleship to get underway during the attack, her crew desperate to escape the inferno of Battleship Row. But fires from bomb hits and strafing runs spread faster than her damaged control parties could contain them, with flames threatening to reach her magazines and create another catastrophic explosion like Arizona's. Her captain made the agonizing decision to beach the ship rather than risk blocking the harbor channel. Nevada ran aground off Hospital Point, still burning, her attempted escape thwarted by fires that could not be controlled. The pattern was clear and damning. In a single morning, the United States Navy lost more ships to fire and its secondary effects than to direct enemy action alone. Bombs and torpedoes started fires, but it was the Navy's inability to control those fires that turned survivable damage into total loss. Ships that should have been saved were instead consumed by flames that spread unchecked through steel corridors, ignited ammunition magazines, and overwhelmed damage control parties armed with inadequate tools and obsolete techniques. Among those who studied the disaster with particular interest was Lieutenant Harold J. Burke, a Navy reservist who had spent 20 years with the New York City Fire Department before being called to active duty. His path to this moment had been shaped by decades of brutal experience fighting fires in one of America's most demanding urban environments. Harold J. Burke had joined the FDNY in the early 1920s, entering a fire service still dominated by horse-drawn apparatus and techniques that had changed little since the previous century. New York in those years was a city of extremes, gleaming skyscrapers rising in Manhattan, while tenements packed with immigrants crowded the Lower East Side, modern department stores filled with the latest goods, while warehouses stuffed with combustible materials lined the waterfront. Working his way up to the ranks during a transformative period in American firefighting, Burke fought blazes in 5-story walk-up tenements, where families lived packed 20 to a floor, buildings with wooden interior construction that burned like kindling once fire took hold. He battled warehouse fires where burning turpentine, paint, and industrial chemicals created infernos that conventional firefighting methods could barely touch. Through these experiences, he learned that different fires required different approaches, that what worked on burning wood might spread flames through burning liquids, that sometimes less water applied correctly accomplished more than torrent applied incorrectly. By the time war clouds gathered in the late 1930s, Burke had risen to deputy chief of the FDNY, one of the most demanding firefighting positions in America. As deputy chief, he oversaw operations across multiple boroughs, coordinating responses to major fires and developing standardized procedures that could be applied consistently across the department. He was responsible for training, equipment acquisition, and tactical doctrine, experience that would prove invaluable when applied to naval firefighting. The FDNY of Burke's era was at the forefront of firefighting innovation. Municipal fire departments fought fires daily, learning through painful experience what worked and what failed. They experimented with new equipment, refined techniques, and shared knowledge across departments. By 1940, progressive fire departments had largely adopted fog nozzles for specific applications, particularly fires involving flammable liquids, where solid streams proved not just ineffective but actively dangerous. Burke had witnessed firsthand how fog nozzles transformed outcomes in industrial fires. He had seen burning warehouse fires that solid streams only brought under control within minutes once fog patterns were applied. He had watched petroleum fires that conventional tactics could not touch extinguished by the steam-generating capability of properly applied water fog. His understanding of the physics, heat absorption, and steam generation, the tactical applications of water curtains and indirect application, the importance of cooling superheated gases before attempting interior attacks, set him apart from officers whose knowledge came purely from naval tradition. When Burke received his commission as a Navy lieutenant and reported for active duty, he brought with him this wealth of practical knowledge. His initial assignment was to inspect damage control procedures aboard ships in port, evaluating their readiness for combat operations. What he found alarmed him profoundly. Naval firefighting in 1941 remained rooted in traditions established during the Age of Sail. The basic approach had changed remarkably little over centuries. When fire broke out, sailors formed bucket brigades to pass water hand to hand from a nearest source. When pumps were available, they directed solid streams of water at the base of flames through straight-bore nozzles that had barely evolved since the 1800s. The emphasis was on volume. Pour enough water on any fire, and eventually it must go out. This doctrine worked adequately for the fires most likely to occur on wooden ships, burning canvas, smoldering rope, fires in crew quarters or storage spaces. The fires were relatively small, contained within compartments that could be sealed off, and generally involved ordinary combustibles that responded to cooling from water application. Naval tradition emphasized aggressive interior attacks, getting as close to fire as possible with the largest hose capable of fitting through passageways and overwhelming flames with sheer volume of water. But modern warships bore little resemblance to their wooden ancestors. Steel construction meant fires behaved differently. with metal conducting heat throughout structures and creating superheated spaces that were death traps for firefighters. The introduction of aviation operations on carriers brought massive quantities of aviation gasoline aboard, stored in tanks distributed throughout the ship, and pumped through miles of piping to fueling stations on hangar and flight decks. A single carrier might carry over 150,000 gallons of aviation gasoline, along with bombs, rockets, and ammunition for dozens of aircraft. The vulnerability this created was staggering. Yet the Navy's firefighting doctrine had not evolved to match the threat. Inspecting ships equipped with fire mains and hydrants positioned throughout, Burke found straightbore nozzles of various sizes, from small handheld types to massive monitors capable of delivering thousands of gallons per minute. He observed damage control parties trained to stretch hoses, connect to hydrants, and direct solid streams of fires. What he did not find was any recognition that solid streams were fundamentally inadequate for the types of fires modern naval warfare would create. When he questioned damage control officers about procedures for fighting aviation gasoline fires, he received answers that revealed dangerous ignorance. They would direct solid streams at the base of flames, they explained, overwhelming the fire with volume. When Burke pointed out that solid streams scatter burning gasoline and spread fire rather than extinguishing it, he was met with blank stares or irritation at civilian interference with naval traditions. The Navy's damage control schools taught bucket brigade procedures unchanged since wooden ships. They emphasized the importance of maintaining pressure in fire mains, of organizing men efficiently to stretch hoses, of directing streams at the seat of fire. They taught almost nothing about the behavior of different types of fires, about the physics of heat transfer and steam generation, about the dangers of applying water to burning liquids, about the importance of cooling superheated spaces before entry. Burke submitted report after report documenting these deficiencies, recommending adoption of fog nozzles and modernized training. His reports were filed away, acknowledged with perfunctory responses, but producing no actual changes. The Navy had been fighting fires the same way for generations. Why should they change now based on the recommendations of a civilian firefighter who had never served at sea? Then came Pearl Harbor, and everything changed. In the days and weeks following December 7th, damage assessment teams fanned out across Pearl Harbor to document what had happened and why. They photographed destroyed ships from every angle, interviewed survivors, examined burned compartments, and attempted to reconstruct the sequence of events that had turned survivable damage into catastrophic loss. Obtaining copies of these reports and photographs through his position in the Navy's Damage Control Assessment Office, Burke saw confirmation of his worst fears. Ship after ship showed the same pattern. Initial damage from bombs or torpedoes was followed by fires that spread out of control, overwhelming damage control parties, and ultimately dooming vessels that should have survived. The photographs told stories of desperate improvisation and tragic failure. Firefighting teams had attacked fires with solid streams, only to watch flames spread as water scattered burning oil across decks and into adjacent compartments. They had directed powerful streams into burning spaces, only to create so much flooding that ships capsized or sank before fires could be controlled. They had been driven back again and again by heat and smoke they had no way to cool or dissipate, forced to watch helplessly as flames consumed their ships. Survivor accounts provided even more damning evidence. Sailors described attacking fires with the largest hoses they could deploy, pouring thousands of gallons into burning spaces, only to watch flames intensify as water pressure scattered burning petroleum. They described being unable to approach within 50 feet of fires because radiant heat was too intense, unable to cool spaces enough to make entry. They described ammunition cooking off because they had no way to cool magazines threatened by adjacent fires, explosions that killed firefighting personnel and spread fire to new areas. Most tellingly, they described the psychological impact of facing fires they had no effective means to fight. Training had taught them that solid streams were the answer to any fire. When those streams failed, when fires grew despite their efforts, sailors experienced a profound sense of helplessness. Some abandoned firefighting efforts prematurely, convinced nothing could stop the flames. Others persisted beyond the point of safety, dying in futile attempts to control fires with inadequate tools. Compiling this evidence into a comprehensive report arguing for immediate adoption of fog nozzles and complete overhaul of naval firefighting training, Burke documented municipal firefighting experience with similar fires, provided data on fog nozzle effectiveness against burning petroleum, explained the physics of why fog patterns succeeded where solid streams failed, and outlined a training program that could transform naval damage control capabilities within months. His report landed on desks throughout the Bureau of Ships and the Navy's Training Command. Once again, it was met with skepticism bordering on hostility. Officers questioned whether municipal firefighting experience was relevant to shipboard conditions. They argued that fog nozzles looked inadequate, that the fine mist appeared to be less water and therefore less effective. They suggested that better training in traditional methods was all that was needed, not wholesale equipment changes. The institutional resistance Burke faced was rooted in multiple factors. Adopting his recommendations would require admitting that Pearl Harbor losses were partly due to inadequate doctrine, not just a prize attack. It would mean replacing equipment fleet-wide at significant cost. It would require rewriting training manuals and retraining thousands of sailors. Most fundamentally, it would challenge naval traditions that stretch back centuries, traditions that defined institutional identity and professional pride. Finding himself fighting not just technical ignorance, but cultural inertia, bureaucratic self-protection, and the natural human resistance to admitting error, Burke's recommendations were revolutionary, and revolutions are never welcomed by established institutions, even when evidence demands change. While Burke fought his bureaucratic battles, the war continued and ships continued to burn. Each new loss provided fresh evidence that traditional firefighting methods were inadequate, but also created pressure to focus on building new ships rather than changing how fires were fought on existing ones. On May 8, 1942, carrier Lexington succumbed to uncontrolled fires following damage at the Battle of Coral Sea. The carrier had survived multiple torpedo and bomb hits during the battle, damage that was serious but should have been survivable. Her damage control parties fought the initial fire successfully, and for several hours it appeared the ship might be saved. Then fuel vapors that had accumulated in compartments damaged by torpedoes found an ignition source, triggering a massive explosion that started fires deep in the ship's interior. Firefighting teams attacked these new fires with solid streams, but the flames were fed by leaking aviation gasoline and hydraulic fluid that solid streams could not effectively extinguish. Heat built up in compartments adjacent to the fires, cooking off ammunition and starting secondary fires faster than crews could contain them. Within hours, fires were burning out of control through multiple decks. Explosions rocked the ship as magazines detonated. 216 men died before Lexington had to be abandoned and scuttled. A capital ship, one of only 4 fleet carriers available to the Pacific Fleet, was lost not to enemy action alone, but to the Navy's inability to control the fires that followed initial damage. On September 15, 1942, carrier Wasp was torpedoed by Japanese submarine I-19 southeast of San Cristobal Island in the Solomons. 3 torpedoes struck the carrier's starboard side, rupturing aviation gasoline tanks and starting massive fires on the hangar deck. Aviation gasoline poured from ruptured tanks, creating pools of burning fuel that spread across the hangar deck and into adjacent spaces. DC parties directed solid streams at these fires, but the high-pressure water scattered burning gasoline, spreading flames rather than extinguishing them. Within 30 minutes, fires were burning on 3 decks. Ammunition began cooking off, killing damage control personnel and preventing close approach to the fires. The ship lost electrical power, meaning pumps could not maintain adequate pressure in fire mains. Firefighting teams continued fighting with reduced water pressure, but solid streams that were barely effective at full pressure accomplished nothing at half pressure. Heat built to levels that began warping steel structures. After 3 hours of futile firefighting efforts, the order was given to abandon ship. 193 men were killed. Wasp was scuttled by destroyer torpedoes. Another carrier lost to fires that should have been controllable. The pattern repeated with smaller vessels. Destroyers hit by bombs or torpedoes found their damage control parties overwhelmed by fires that spread faster than they could be contained. The close quarters on destroyers meant fires could reach magazines within minutes, creating catastrophic explosions. Cruisers survived torpedo hits only to be consumed by fires that traditional methods could not control. Each loss provided more evidence that Burke's warnings were correct, but institutional inertia continued to prevent change. By late 1942, the mounting toll of ships lost to fire was becoming impossible to ignore. Admiral Ernest King, Commander-in-Chief of the U.S. Fleet, demanded answers about why so many damaged ships were being lost to fire rather than saved by damage control. His inquiries put pressure on the Bureau of Ships to produce results, to explain why the Navy seemed unable to control fires that municipal fire departments routinely handled. This created an opening for Burke, but he needed an ally with sufficient authority to force change through bureaucratic resistance. That ally, Cochrane, was an engineer by training, a 1911 Naval Academy graduate who had specialized in ship construction and propulsion systems throughout his career. Unlike many flag officers whose experience was primarily operational, Cochrane understood technical systems at a deep level. He had overseen destroyer construction during World War I, served as supervisor of shipbuilding at multiple yards, and earned a reputation for innovation and willingness to challenge conventional wisdom when engineering principles demanded it. Cochrane's appointment came at a critical moment. The Navy was in the midst of the largest shipbuilding program in history, with hundreds of new vessels under construction. But ships being lost to fire at sea threatened to undermine this massive investment. Cochrane immediately demanded a comprehensive review of damage control capabilities, particularly firefighting equipment and training. Seeing his opportunity, Burke arranged a meeting with Cochrane through intermediaries to present his case for fog nozzles. The meeting did not go as Burke initially expected. Cochrane listened to Burke's arguments about fog nozzle superiority, then peppered him with technical questions that revealed a sophisticated understanding of thermodynamics, fluid mechanics, and heat transfer. How exactly did fog patterns increase heat absorption rates? What were the optimal droplet sizes for different fire conditions? How did steam generation rates compare between fog and solid streams at various pressures? Burke answered each question, providing not just theoretical explanations, but practical examples from his FDNY experience. He described specific fires where fog nozzles had succeeded after solid streams failed, explained the tactical applications in different scenarios, and acknowledged the limitations of fog nozzles in situations where solid streams remained superior. Cochrane was impressed by Burke's command of technical details and his practical experience, but he remained skeptical. The fog nozzle's fine mist looked inadequate. How could something that appeared to deliver less water actually be more effective? Burke explained the physics of surface area and heat absorption, but Cochrane needed more than explanations. He needed proof. "Lieutenant, the Navy doesn't change equipment and doctrine based on theories and municipal experience," Cochrane told Burke. "If you want to consider this seriously, you need to demonstrate that fog nozzles actually work better than solid streams under controlled conditions where we can measure results." Burke immediately agreed. "Give me a week to set up a demonstration, Admiral. I'll prove it works." Burke spent the next week preparing the most important demonstration of his life. He arranged for a controlled burn facility at a naval yard where realistic fires could be created safely. He obtained aviation gasoline, the same 100-octane fuel that powered carrier aircraft, and created the most dangerous fires at sea. He built a mock-up compartment that replicated the steel construction, confined spaces, and limited ventilation found aboard ship. He assembled damage control equipment, solid-bore nozzles of various sizes, and several Rockwood fog nozzles. He recruited experienced firefighters from both the FDNY and Navy damage control schools to serve as operators, ensuring that any differences in results would be due to equipment, not operator skill. Most critically, he installed measurement instruments to quantify results objectively. Thermocouples placed throughout the compartment would measure temperatures before, during, and after water application. Flow meters would record exactly how much water was used. Timers would document how long it took to achieve knockdown and complete extinguishment. Burke wanted data that could not be dismissed as subjective opinion. Cochrane arrived for the demonstration, accompanied by several senior officers from the Bureau of Ships and the Navy's Training Command. Some were genuinely interested in seeing Burke's claims validated or refuted. Others attended expecting to witness the failure of civilian meddling in naval traditions, looking forward to dismissing fog nozzles once and for all. Burke began with a presentation explaining what they would witness. "Gentlemen, we will conduct 3 burns in this compartment. The first will be extinguished using a 2.5-inch solid stream, standard Navy damage control equipment operated by experienced personnel. The second will be extinguished using a fog nozzle on the same size hose, operated by equally experienced personnel. The third will be a side-by-side comparison with both methods attempted simultaneously. In each case, we will ignite 20 gallons of aviation gasoline, enough to create a serious fire, but small enough to be safely controlled. The first burn began. Aviation gasoline was spread across the steel deck and ignited, creating an instant inferno that filled the compartment with flames and black smoke. The heat was intense. Observers standing 20 feet from the compartment entrance could feel radiant heat on their faces. A damage control team wearing protective gear advanced with a solid stream, directing high-pressure water at the base of the flames. The result was exactly what Burke had predicted. The high-pressure stream hit the burning gasoline and scattered it, spreading fire across a wider area. Some of the water passed through the flames without absorbing much heat, simply running off as waste. Visible flames diminished slightly where the stream directly impacted, but flared higher in areas where scattered gasoline found new fuel sources. After 2 minutes of continuous application, the fire was still burning across most of the compartment floor. After 5 minutes, it was finally out, but the compartment was flooded with several inches of water. Temperatures remained dangerously high, and the method had clearly struggled to control a relatively small fire. Note the time to extinguishment, Burke told the observers. 5 minutes, 7 seconds. Note also the water usage, 420 gallons. Note the compartment remains too hot for safe entry, over 400 degrees Fahrenheit, and note the flooding, which on a damaged ship could contribute to stability problems. The second burn used the same fuel load in the same compartment, now dried and prepared for another test. This time, Burke's team advanced with a fog nozzle, setting it to wide-angle fog pattern. They directed the fog not directly at the flames, but slightly above them, creating a blanket of water droplets that fell to the fire zone while simultaneously cooling the superheated air and smoke in the upper part of the compartment. The effect was dramatic. Within 30 seconds, flames visibly diminished throughout the compartment. Within 60 seconds, they were reduced to small pockets. Within 90 seconds, the fire was completely out. Burke's team then swept the fog pattern across the overhead and bulkheads, cooling the entire space. When they emerged, thermocouples showed compartment temperature had dropped from over 1,200 degrees to less than 300 degrees. Time to extinguishment, Burke announced, 1 minute, 32 seconds. Water usage, 75 gallons. Compartment temperature reduced to safe entry levels, minimal flooding. This is the difference, gentlemen. The fog pattern provides vastly more surface area for heat absorption, converts water to steam more efficiently, and achieves better results with less water. The third demonstration put both methods side by side. 2 teams entered the burning compartment simultaneously, one with solid stream, one with fog nozzle. The fog team achieved knockdown in under a minute. The solid stream team was still fighting scattered pockets of fire 3 minutes later when the exercise was terminated. Cochrane had seen enough. The data was undeniable. Fog nozzles extinguished the fires faster, with less water, and left spaces cooler and safer. The visual difference was equally compelling. What it looked like inadequate mist had proven far more effective than impressive-looking solid streams. "Lieutenant Burke," Cochrane said, "I'm convinced. The question now is how fast we can re-equip the fleet and retrain our sailors." Several of the other officers present tried to raise objections. Fog nozzles might work in controlled conditions, but would fail in combat chaos. Sailors could not be trained to use them effectively. The cost of re-equipping hundreds of ships was prohibitive, but Cochrane cut them off. "I just watched fog nozzles extinguish fires 3 times faster using 1/5 the water. Every day we delay adopting this equipment, we risk losing more ships and sailors to fires that could be controlled. We're implementing this immediately. Lieutenant Burke, you're hereby tasked with establishing a fleet-wide training program. You'll have whatever resources you need." Immediately facing the challenge of transforming his demonstration into a fleet-wide training program, Burke confronted an enormous task. Thousands of sailors needed training. Dozens of training facilities needed to be built. Hundreds of instructors needed to be prepared. Traditional military training timelines measured such transformations in years. Burke had months at best before the fleet would need these skills in combat. His first step was recruiting help. Through Navy personnel channels, Burke identified Lieutenant Kilduff, a reservist who had served with the Boston Fire Department before the war. Kilduff had experience both as a firefighter and as a training instructor, having run the Boston FD's Recruit Academy for several years. Together, Burke and Kilduff formed a core team that would revolutionize naval damage control training. Their approach was revolutionary for military training of that era. Rather than classroom instruction followed by limited practical exercises, Burke and Kilduff designed a program built around realistic fire training that put sailors into conditions as close to actual shipboard fires as safely possible. They believed that confidence came from experience, that sailors who had successfully fought realistic training fires would perform effectively in combat. The first training facility opened at Boston Naval Yard in June 1942 at the Navy's K Street Annex in South Boston. Burke and Kilduff spent weeks designing and building the training props. They constructed full-scale mock-ups of ship compartments using steel bulkheads, overheads, and decks salvaged from scrap vessels. These compartments replicated confined spaces, limited access, and restricted ventilation found aboard ship. They installed realistic fire scenarios using controlled fuel burns that could create intense heat and smoke without endangering students beyond acceptable limits. The centerpiece was a hangar deck mock-up that could simulate an aviation gasoline fire like those that had doomed Lexington and Wasp. The structure was 50 feet long and 30 feet wide with a steel deck and overhead, ventilation systems that could be secured to replicate battle damage, and fuel delivery systems that could create pools of burning gasoline across the deck. Safety systems included emergency cutoffs, fire suppression systems, and escape routes, but students experienced realistic flames, heat, and smoke. Other training props included an engine room mock-up with fuel oil fires, a berthing compartment with Class A combustibles burning, and a series of small compartments for teaching basic firefighting techniques. Each prop was instrumented to allow instructors to monitor conditions and ensure safety while pushing students to their limits. The training curriculum Burke and Kilduff developed progressed systematically from basic to advanced skills. Day 1 began with classroom instruction on fire behavior, the physics of heat transfer, and the theory behind fog nozzles. Students learned why fog patterns worked, how to adjust nozzles for different conditions, and when solid streams remained the better choice. But classroom time was limited to 4 hours. The rest of the day was hands-on training. Students suited up in protective gear, helmets, gloves, heavy canvas jackets. They learned to don emergency breathing apparatus, to check equipment, to work in teams. Then they entered the small compartment trainer for their first live fire. The instructors ignited a controlled burn, and students practiced approaching the fire, applying fog patterns from a safe distance, advancing as the fire diminished, achieving complete extinguishment. They repeated the evolution multiple times until movements became automatic. Day 2 escalated intensity. Students faced larger fires and more realistic scenarios. They learned to force entry through doors blocked by heat and pressure. They practiced advancing hose lines through smoke-filled passageways. They experienced flashover conditions when superheated gases in a compartment ignite simultaneously, in a controlled environment where instructors could demonstrate how fog patterns prevented flashover by cooling overhead gases. The training was physically and mentally demanding. Temperatures in training compartments reached 500 to 600 degrees Fahrenheit. Smoke reduced visibility to 0. Students learned to work by feel, to trust their training, to function in conditions of extreme stress. Many found it terrifying at first, but instructors pushed them through fear to competence. Day 3 brought the full scenario, fighting a simulated hangar deck fire with aviation gasoline burning, smoke filling the space, and simulated casualties requiring rescue. Students worked in teams, coordinating multiple hose lines, some applying fog to cool spaces, while others advanced to attack flames directly. They learned to communicate in zero visibility, to support each other, to maintain discipline under conditions approaching actual combat. The transformation was remarkable. Sailors who had never fought a fire in their lives arrived skeptical or frightened. They left confident, having repeatedly knocked down intense fires using techniques that worked. Many later reported that combat fires, while more dangerous due to enemy action and actual casualties, were psychologically easier because they had experienced similar conditions in training. Burke and Kilduff personally trained the first cadre of 260 instructors through an intensive 3-week program. These instructors would fan out to establish firefighting schools at every major continental naval base. The selection criteria for instructors were demanding. They needed firefighting experience, teaching ability, technical understanding, and leadership skills. Many were drawn from municipal fire departments, reservists like Burke and Kilduff who brought civilian expertise into military service. The instructor training program covered not just firefighting techniques, but teaching methods, safety procedures, prop maintenance, and student evaluation. Burke emphasized that instructors needed to balance safety with realism, to push students hard enough to build real confidence without creating unnecessary risk. He shared lessons from his FDNY experience about teaching firefighting skills, about building muscle memory through repetition, about the psychology of fear and how to overcome it. As instructors graduated and dispersed to other bases, the program replicated systematically. San Diego Naval Base opened its firefighting school in August 1942. Norfolk followed in September. By the end of 1942, firefighting schools were operating at Great Lakes, Charleston, Seattle, Pearl Harbor, and a dozen other major bases. Each school used identical training props built to Burke's specifications, ensuring consistency fleet-wide. The standardization was critical. A sailor trained in Boston used identical techniques, equipment, and tactical approaches to one trained in San Diego. When ships from different squadrons operated together, their damage control parties could coordinate seamlessly. Officers could assume that any properly trained sailor would respond to fires using proven methods, allowing for predictable planning and coordination during battle damage situations. The training program expanded to include officers in dedicated courses covering firefighting tactics, damage control coordination, and leadership during fire emergencies. Burke insisted that officers understand not just what to order, but why. That they be able to evaluate firefighting effectiveness and make informed decisions under pressure. Officer training included tabletop exercises, where they managed multiple simultaneous fires, allocated resources, and made triage decisions about which fires to fight first. By mid-1943, the training program was producing results. Thousands of sailors had been trained in fog nozzle techniques. Ships deploying to combat theaters carried crews confident in their ability to fight fires effectively. The psychological transformation was as important as the technical skills. Sailors no longer viewed fire as an overwhelming force, but as an enemy they had been trained to defeat. Training alone would not save ships. The fleet needed fog nozzles in sufficient quantities to equip every vessel, and production needed to happen quickly despite wartime manufacturing constraints. The Bureau of Ships moved aggressively to contract for fog nozzle production, placing orders with multiple manufacturers to ensure rapid delivery and build redundancy into the supply chain. Rockwood Sprinkler Company became the primary contractor for the Rockwood all-purpose fog nozzle, the design Burke had championed. The company's factory in Worcester, Massachusetts geared up for mass production, hiring additional workers and adding shifts to meet Navy demands. By early 1943, Rockwood was producing thousands of nozzles monthly. The Bureau of Ships standardized on 2 sizes, nozzles for 1.5-inch hose and nozzles for 2.5-inch hose. This simplified logistics and training. Every ship would carry both types, with the smaller nozzle for general use and the larger for major fires. The 3-position design, fog, solid stream, and shutoff, gave sailors tactical flexibility. Extension applicators allowed firefighters to reach into spaces too dangerous for direct entry, directing fog through doorways or ventilation openings. Manufacturing the nozzles required precision machining. The internal mechanisms that broke water into fog patterns needed to be manufactured to tight tolerances to function reliably at the pressures and flow rates required. Quality control was critical. A nozzle that failed in combat could cost lives. Rockwood implemented rigorous testing, pressure testing each nozzle and visually inspecting fog patterns before shipping. Distribution logistics challenged the Navy's supply system. New construction ships were easiest. Fog nozzles were installed as part of initial damage control equipment packages. Ships already in service needed retrofitting, which meant delivering nozzles to forward bases where ships operated. The Navy established dedicated supply channels for damage control equipment, prioritizing fog nozzles for rapid distribution. Ships in the Pacific Theater received nozzles through the Fleet Logistics System that supplied everything from ammunition to replacement parts. Supply ships carried fog nozzles to forward anchorages at Ulithi, Eniwetok, and Pearl Harbor. Ships pulled into these bases for resupply and maintenance received fog nozzles as a priority item. By late 1943, most frontline combatants had received at least partial equipment. By mid-1944, coverage was nearly universal. The transition from solid streams to fog nozzles was not absolute. Traditional solid-bore nozzles remained aboard as backup equipment and for specific applications where they retained advantages. Solid streams were superior for certain scenarios, firefighting from a distance, cooling structures externally, or when maximum reach was needed. Burke had never advocated eliminating solid streams entirely, only ensuring that fog nozzles were available as the primary tool for the most dangerous shipboard fires. Damage control stations throughout ships were reconfigured to store fog nozzles prominently, with extension applicators, spare parts, and cleaning equipment. Maintenance procedures were developed and taught. Fog nozzles required regular cleaning to prevent salt buildup that could clog the fine passages that created fog patterns. Sailors learned to disassemble, clean, and reassemble nozzles, to test them periodically, to identify and replace worn parts. The material cost of equipping the fleet was substantial but not prohibitive. Fog nozzles were relatively inexpensive compared to other naval equipment. Each nozzle cost approximately $75, compared to millions for major weapon systems. A destroyer might carry 20 nozzles for a total equipment cost of $1,500. A carrier might carry 60 for $4,500. Across the entire fleet, the total investment was measured in hundreds of thousands of dollars, trivial compared to ship construction costs and inconsequential compared to the value of ships and lives saved. That was measured in hundreds of thousands of dollars, trivial compared to ship construction costs and inconsequential compared to the value of ships and lives saved. The first combat tests of Burke's program came in scattered incidents throughout 1943 and early 1944. Ships took damage, fires erupted, and damage control parties trained in fog nozzle techniques saved vessels that might otherwise have been lost. Each success built confidence and reinforced the value of the training and equipment transformation. In November 1943, the light cruiser Birmingham took a torpedo hit that ruptured fuel tanks and started fires in 2 engineering spaces. DC parties attacked the fires with fog nozzles, using indirect application through ventilation ducts to cool spaces too hot for direct entry. The fires were controlled within 40 minutes, and Birmingham continued operations after temporary repairs. Previous doctrine would likely have required flooding the compartments, potentially dooming the ship. Fog nozzles provided a more effective alternative. In January 1944, the destroyer spent survived bomb hits during operations in the Gilbert Islands. The bombs penetrated the main deck and exploded in crew berthing areas, starting fires that spread rapidly through the wooden furniture and bedding that filled these spaces. Firefighting teams used fog patterns to cool adjacent spaces and prevent fire spread while attacking the main fire directly. The combination of rapid knockdown and minimal water usage allowed Spence to maintain stability and return to port under her own power. The destroyer Laffey provided perhaps the most dramatic early validation of fog nozzle effectiveness. On April 16, 1945, off Okinawa, Laffey endured one of the most intense kamikaze attacks of the war. In just 80 minutes, the destroyer was hit by 4 bombs and crashed by 6 kamikaze aircraft. Each impact started fires. The crew fought these fires continuously throughout the attack, using fog nozzles to suppress flames even as additional kamikazes struck the ship. The fires were fed by aviation gasoline from crashed aircraft, ruptured fuel lines, and burning debris. Traditional solid streams would have scattered this burning fuel, likely spreading fires faster than they could be contained. Fog patterns extinguished burning gasoline without spreading it, cooled spaces threatened by fire spread, and used minimal water, preventing flooding that could have capsized a heavily damaged destroyer. Laffey survived with 32 killed and 71 wounded. The ship was heavily damaged but remained afloat and was eventually repaired. Her survival under such intense attack, with fires burning across multiple locations simultaneously, demonstrated that properly trained damage control parties using effective equipment could save ships even under extreme circumstances. Laffey's experience became legendary in the fleet, proof that damage control training and fog nozzles worked even in the worst conditions imaginable. The battleship South Dakota provided another validation. In June 1944, a bomb hit during operations in the Marianas penetrated to a handling room where ready ammunition for anti-aircraft guns was stored. The bomb explosion ignited powder charges, starting a fire that threatened to reach the main magazines below. If those magazines detonated, South Dakota would have been destroyed. Firefighting teams attacked the fire using fog nozzles with extension applicators, directing fog through openings in the deck to reach flames below. The fog cooled the space and generated steam that displaced oxygen, smothering flames before they could reach the main magazines. Simultaneously, other parties used fog to cool the magazines themselves, reducing temperatures and preventing sympathetic detonation. The fire was controlled in 35 minutes, and South Dakota continued operations. Traditional methods might not have allowed close enough approach to prevent magazine detonation. The carrier Hancock survived a kamikaze hit on April 7, 1945 off Okinawa that penetrated the hangar deck and exploded among parked aircraft. The explosion ignited aviation gasoline and started fires that spread through the hangar. DC parties used both direct fog application and indirect fog through ventilation systems to attack flames from multiple directions simultaneously. The hangar deck sprinkler system had been damaged by the explosion, so fog nozzle provided the primary firefighting capability. The fire was controlled in 70 minutes. 62 men were killed and 71 wounded, but Hancock remained operational and continued launching strikes within hours. These incidents and dozens of others validated Burke's transformation of naval firefighting. Ships that should have been lost were saved. Casualties that would have been catastrophic were reduced to manageable levels. The fleet's operational capability was maintained even under intense enemy attack. Word spread through the fleet about fog nozzle effectiveness, building confidence and enthusiasm for the techniques Burke had championed. USS Franklin had already proven the value of fog nozzles before her near destruction in March 1945. On October 30, 1944, while operating off the Philippines during the Battle of Leyte Gulf, Franklin took her first major hit. A Japanese kamikaze aircraft evaded the combat air patrol and crashed to the flight deck, penetrating to the hangar deck where it exploded among 33 aircraft that were being prepared for strikes. The explosion was catastrophic. Aviation gasoline from ruptured aircraft fuel tanks ignited instantly, creating a fireball that filled the hangar. Bombs and rockets stored on the aircraft began cooking off, adding explosions to the fire. Ready ammunition for aircraft guns detonated, sending shrapnel throughout the hangar space. Within minutes, fires were burning across the entire hangar deck. Franklin's damage control parties had been trained in Burke's methods. They responded immediately with fog nozzles, establishing a coordinated attack on the fires from multiple directions. Teams positioned themselves at hangar deck access points and directed fog patterns into the space, cooling superheated gases and creating conditions where direct entry became possible. Other teams used extension applicators to reach areas too hot for direct approach, directing fog through ventilation openings and damaged sections of the hangar deck. The fog patterns prevented fire spread to adjacent spaces, while teams attacked the main body of fire. The combination of multiple fog streams working together, creating steam that displaced oxygen while cooling structures, proved devastatingly effective against the inferno. The battle to save Franklin that October day lasted 2.5 hours. Temperatures in the hangar exceeded 2,000 degrees Fahrenheit, hot enough to warp steel beams and melt aluminum components. Traditional solid streams would have been ineffective at those temperatures. The water would have flashed the steam before reaching the seat of the fire, providing little cooling effect. Fog patterns, already optimized for steam generation, provided maximum cooling efficiency even at extreme temperatures. The damage control parties worked in shifts, rotating men out as they reached the limits of heat exhaustion, bringing in fresh teams to maintain continuous firefighting. They advanced systematically, cooling spaces section by section, extinguishing fires in areas that had been brought under control while preventing reignition. By 1500 hours, all major fires were out. By 1700 hours, hot spots had been extinguished and temperature reduction allowed damage assessment teams to enter the hangar. 56 men were killed and 60 wounded in the October attack, most in the initial explosion and immediate aftermath. But Franklin survived and was able to withdraw under her own power. Temporary repairs were made at Ulithi, and the carrier returned to combat operations within 3 weeks. The official damage report credited fog nozzle application and effective damage control training as critical factors in saving the ship. This October experience provided crucial lessons for Franklin's crew. They learned their training worked under combat conditions. They identified areas for improvement in coordination and communication. They gained confidence that even severe fires could be controlled with proper techniques. This experience would prove invaluable 5 months later, when Franklin faced damage that should have destroyed her. The ultimate test of Burke's transformation came on March 19, 1945, when USS Franklin suffered damage that should have destroyed her. The carrier was operating 50 miles off the Japanese coast, part Task Force 58, conducting strikes against airfields on Kyushu in support of the Okinawa invasion. At 0708 hours, a single Japanese dive bomber penetrated low through heavy overcast, evading radar detection until it was too close for effective anti-aircraft fire. The bomber dropped 2 bombs that struck Franklin's flight deck and hangar deck in the worst possible locations at the worst possible time. 31 aircraft were spotted on the flight deck, fully fueled and armed with bombs and rockets, prepared to launch the first strike of the morning. 22 more aircraft filled the hangar deck below, similarly loaded and fueled. The total aviation gasoline aboard these 53 aircraft exceeded 15,000 gallons. The ordnance they carried included tiny Tim rockets, 500-pound bombs, and thousands of rounds of ammunition. The first bomb penetrated the flight deck, near the centerline, and detonated on the hangar deck. The explosion instantly ignited every aircraft in the hangar space. Aviation gasoline sprayed across the deck as fuel tanks ruptured, creating a lake of fire that spread throughout the 400-foot-long hangar. The intense heat immediately began cooking off ammunition and ordnance on the burning aircraft. Aft near the number 3 elevator, the second bomb penetrated the gallery deck, detonating in crew berthing areas and killing dozens of men instantly while starting fires on 3 decks. Fuel lines ruptured, feeding additional gasoline into the fires. The explosion also damaged critical systems, including fire mains, electrical distribution, and communication systems. Within 2 minutes, a dozen tiny Tim rockets broke loose from their mounts on burning aircraft. These massive 11-foot-long rockets, each carrying a 138-pound warhead, became unguided missiles ricocheting around the hangar deck. They struck bulkheads, penetrated through to adjacent spaces, and exploded when their warheads hit hard enough to detonate them. Each explosion started new fires and sent shrapnel throughout nearby compartments. Machine gun ammunition began cooking off by the hundreds of thousands of rounds. The sustained fusillade of bullets tore through thin bulkheads, wounded or killed anyone in the vicinity, and made the hangar deck a death trap. Larger ordnance started detonating as fires reached bombs and rockets on aircraft. Each explosion sent shock waves through the ship, triggered more fires, and generated fireballs that spread flames to new areas. The casualties in the first 10 minutes were horrific. The initial explosions killed approximately 300 men instantly. Flight deck crews spotting aircraft, hangar deck personnel preparing planes, and sailors in berthing areas near the second bomb impact. Hundreds more were wounded, many critically burned. Dozens were blown overboard or jumped into the sea to escape the inferno. The ship's medical facilities were quickly overwhelmed. Franklin's propulsion system was lost when engineering spaces filled with smoke, forcing their evacuation. The ship went dead in the water, drifting 50 miles from the Japanese coast with fires burning across 4 decks. Radio communications were destroyed, preventing calls for assistance. A list developed as water from ruptured fire mains and firefighting accumulated on the starboard side, reaching 13 degrees and threatening to increase further. In these desperate circumstances, Lieutenant Commander Joseph T. O'Callaghan, the ship's Catholic chaplain, and Lieutenant Donald A. Gary, an engineering officer, organized a firefighting effort that would save Franklin. O'Callaghan moved through the ship, gathering anyone still able to fight, cooks, clerks, storekeepers, anyone not already engaged in fighting fires or treating casualties. Gary organized rescue parties to reach men trapped below by fire and smoke. They grabbed fog nozzles and advanced into conditions that would have been impossible with traditional equipment. Many of the ship's fire mains were ruptured, meaning water pressure was far below normal levels. Electrical power was lost, eliminating pumps that normally maintain pressure. The hangar deck sprinkler system had been destroyed. The damage control parties had to work with whatever water pressure they could get, using portable pumps supplemented by bucket brigades in areas where mains were completely failed. Under these circumstances, fog nozzles proved their worth decisively. Solid-bore nozzles required substantial water pressure to function effectively. At reduced pressure, they would have been nearly useless. Fog nozzles operated effectively even at reduced pressure, converting whatever water was available into fog patterns that cooled spaces and smothered flames. The firefighting effort became a sustained battle lasting 8 hours. Teams attacked fires systematically, establishing priorities based on which fires threatened the most critical spaces. The forward magazines were the highest priority. If those detonated, Franklin would be destroyed instantly. Fog application through ventilation ducts cooled these spaces enough to prevent detonation even as fires raged in adjacent compartments. When direct approach to fires was impossible due to heat or continuing explosions, teams used extension applicators to direct fog through doorways, ventilation openings, and damaged sections of hull. The fog cooled spaces from a distance, gradually reducing temperatures until direct entry became possible. Teams worked in rotation, fighting until exhausted, then pulling back to recover while fresh teams took over. Gary led rescue parties into spaces where 300 men were trapped 3 decks below the hangar. The only route led through passageways where temperatures exceeded 500 degrees and smoke reduced visibility to 0. Gary's teams advanced using fog nozzles to create protective water curtains, the fog cooling air temperature enough to allow brief penetration into otherwise lethal conditions. They made 7 trips into that inferno, each time leading groups of trapped men back to safety. 252 men survived because of these rescue efforts. The light cruiser Santa Fe came alongside to provide assistance, a dangerous maneuver that required the 2 ships to operate with their hulls nearly touching. Santa Fe's crew passed across additional fog nozzles, hoses, and portable pumps. Her pumps supplemented Franklin's damaged systems, providing better water pressure for firefighting. Santa Fe also evacuated 833 survivors, taking wounded men aboard for medical treatment and removing non-essential personnel to reduce the load on Franklin's overwhelmed damage control organization. Throughout the day, the battle against fire continued. At multiple points, it appeared Franklin would have to be abandoned. Fires threatened to reach the forward magazines repeatedly, requiring urgent fog application to cool these spaces. Explosions continued as ordnance cooked off, killing firefighters and starting new fires. The list increased as flooding accumulated, reaching 17 degrees before counterflooding could stabilize the ship. But gradually, the tide turned. By afternoon, major fires were under control, though hot spots continued burning. By evening, temperature readings showed spaces were cooling throughout the ship. By nightfall on March 19th, every significant fire was out, though damage control parties would fight flare-ups for days afterward. The final casualty count remained disputed in historical sources. Samuel Eliot Morrison's official naval history of the war cites 724 killed and 265 wounded. Other sources, including the Naval History and Heritage Command, list 807 killed and 487 wounded. The discrepancy stems from different methodologies for counting casualties. Some figures exclude air group personnel or Marines in transit, while others include anyone aboard. Some counts include men who died later from wounds, while others count only immediate casualties. Either figure represents approximately 1/3 of Franklin's crew killed or wounded, the highest casualty rate of any ship that survived the war. But Franklin did survive. Against all odds, despite damage that should have destroyed her, the carrier remained afloat. Over the following days, emergency repairs were made that allowed restoration of partial propulsion. Franklin steamed 12,000 miles under her own power to reach New York, arriving on April 28, 1945. She was a wreck, flight deck buckled and scorched, island structure blackened, side scarred by explosions. But she was afloat, and her surviving crew had brought her home. The official Bureau of Ships analysis of Franklin's survival was unequivocal. Fog nozzles had made the difference between total loss and survival. Without them, the analysis concluded, Franklin would have been abandoned and scuttled within hours of the attack. The fog nozzle's ability to function at reduced water pressure, to cool spaces efficiently with minimal water, to extinguish burning aviation gasoline without spreading it, and to generate steam that smothered fires, all these capabilities that Burke had championed proved decisive. Both O'Callaghan and Gary received the Medal of Honor for their actions saving Franklin, presented at a White House ceremony on January 23, 1946. The citations explicitly mentioned their effective use of damage control equipment, though fog nozzles were not named specifically. Navy training materials subsequently used Franklin's survival as a definitive case study for effective damage control under extreme conditions. The impact of Burke's transformation extended far beyond individual ship survivals. The cumulative effect of improved damage control capabilities altered strategic calculations throughout the Pacific War. Carriers could operate closer to enemy shores, knowing kamikaze damage might be survivable rather than automatically catastrophic. Amphibious forces could accept higher risks during shore bombardment, confident that ships damaged by coastal artillery could likely be saved. The fleet could sustain higher operational tempo because damaged ships returned to service faster. Admiral Chester Nimitz, Commander-in-Chief of the Pacific Fleet, addressed damage control improvements in his post-war assessment of factors contributing to victory. He noted that improved firefighting capabilities, particularly fog nozzle adoption and associated training programs, had been critical to maintaining fleet operational capability during the war's final campaigns when kamikaze attacks created intense pressure on damage control systems. The cumulative lives saved by Burke's program numbered in the thousands. Each ship saved meant hundreds of sailors survived who would otherwise have perished. Franklin alone saved approximately 2,000 men, who were still aboard when the fires were controlled. Had the ship been lost, most would have died. The dozens of other ships saved through effective fog nozzle application each contributed additional lives preserved. The economic impact was equally significant. Each major combatant saved represented millions of dollars in construction costs avoided. A fleet carrier cost approximately $70 million to build and required 2 years from keel laying to commissioning. Saving Franklin alone justified the entire cost of Burke's training program many times over. The cumulative savings from ships that survived rather than being lost ran into hundreds of millions of dollars. Perhaps most importantly, Burke's success demonstrated that innovation could succeed even in tradition-bound military institutions when properly advocated. He had challenged century-old naval doctrine, faced institutional resistance at every level, and ultimately succeeded in forcing wholesale change to equipment and training. His success validated the principle that sometimes the most important military innovations come from outside the military, from civilians who bring different expertise and perspectives. Beyond equipment and training, Burke transformed how the Navy thought about damage control. In 1941, firefighting was viewed as a secondary skill, something done when primary systems failed. By 1945, damage control was recognized as a primary combat capability essential to mission success. Damage control parties became elite teams, trained to the same standards as gun crews and evaluated as rigorously. The psychological shift was profound. Sailors in 1941 viewed fire as an overwhelming force, damage control as a desperate last resort unlikely to succeed. By 1945, sailors approached fires aggressively, confident in their training and equipment, viewing fire as a tactical problem to be solved. This mental transformation from fatalism to confidence represented a fundamental change in naval culture. Officers learned that damage control required the same careful planning and resource allocation as offensive operations. Pre-battle preparations included positioning damage control parties strategically, ensuring equipment was ready and accessible, planning responses to probable damage scenarios. During battle, senior officers monitored damage control efforts as carefully as tactical situations, making decisions about resource allocation and priorities that could determine whether ships survived. The training program created a common culture across the fleet. Sailors trained at different bases using identical techniques, spoke a common language of damage control. Officers could assume standardized capabilities and coordinate effectively even when ships from different squadrons operated together. This standardization extended to equipment maintenance, tactical procedures, and even terminology used to describe firefighting operations. Burke's transformation of naval firefighting occurred alongside parallel developments in Coast Guard firefighting doctrine. Lloyd Layman, who had pioneered indirect fog application techniques as a civilian fire chief before the war, was commissioned as a commander in the Coast Guard and placed in charge of the firefighting school at Fort McHenry in Baltimore. Layman conducted extensive research on fog nozzle applications, using the Liberty ship Gaspar Portola as a test platform. His experiments documented optimal droplet sizes, fog patterns, and application techniques for different fire conditions. He published findings in Fire Engineering magazine in February 1945, providing scientific validation for techniques Burke had championed based on practical experience. After the war, Layman returned to civilian fire service as chief of the Parkersburg, West Virginia Fire Department. He applied the shipboard fog techniques he had perfected during the war to structural firefighting, revolutionizing how municipal fire departments fought fires in buildings. His 1950 presentation, Little Drops of Water, at the Fire Department Instructors Conference demonstrated how indirect fog application could extinguish structure fires more effectively than traditional solid stream attacks. Layman's work ensured that lessons learned in naval combat would transform civilian firefighting globally. The techniques Burke championed for saving ships became standard practice for saving buildings. The fog nozzle became ubiquitous in fire departments worldwide, valued for versatility and effectiveness across multiple fire types. Burke continued serving to the war's end and into the immediate post-war period, training instructors and refining fog nozzle techniques. In July 1947, he was appointed chief of the New York City Fire Department, a position representing the pinnacle of municipal firefighting leadership. He took office on August 1, 1947, but immediately retired from the position upon his appointment. The circumstances of Burke's brief tenure as chief remain somewhat unclear in historical records. Fire Engineering magazine reported on August 1, 1947, that Chief Harold Burke immediately retired upon his appointment. The position remained vacant until Peter J. Loftus was appointed as the new chief on August 1, 1948. During his brief time in the position, Burke influenced the FDNY to adopt training methods developed for the Navy, including realistic fire training props and standardized tactical approaches. Burke's post-war life remains largely undocumented. No death date has been located in accessible records, and his later years remain a mystery. He disappeared from public view after his retirement, leaving behind a legacy measured in ships saved and lives preserved rather than in public recognition or honors. Fog nozzles remain standard equipment in the United States Navy for decades following their adoption. While specific designs evolved and new technologies emerged, the fundamental principles Burke championed, that fine water droplets provide superior cooling and steam generation compared to solid streams, remain foundational to naval firefighting through the remainder of the 20th century. The next major evolution in naval firefighting came following the catastrophic USS Forrestal fire on July 29, 1967, in the Gulf of Tonkin. A Zuni rocket accidentally fired across the flight deck, striking a parked aircraft and rupturing fuel tanks. The resulting fire and explosions killed 134 sailors and airmen and injured 161. The disaster revealed continuing gaps in damage control capabilities, particularly regarding foam firefighting systems for aviation fuel fires. AFFF, aqueous film-forming foam, had been patented by the Navy in 1966, but was not yet deployed fleet-wide. The Forrestal disaster prompted mandatory implementation of AFFF systems throughout the fleet and a complete overhaul of aviation firefighting procedures. Yet fog nozzles remained essential equipment, valued for versatility and effectiveness against multiple fire types. AFFF supplemented fog nozzles rather than replacing them. Through the 1970s and 1980s, fog nozzles remained standard damage control equipment aboard all naval vessels. Successive generations of sailors learned the same basic techniques Burke had introduced, adjusted for new ship designs and evolving fire threats, but fundamentally unchanged in principle. The fog nozzle endured because it worked, because it was versatile enough for multiple applications, and because the physics of heat absorption through water surface area remained constant regardless of technological changes elsewhere. Burke's influence extended far beyond the Navy. Municipal fire departments worldwide adopted fog nozzles following the war, driven by demonstrations of effectiveness in naval applications and by returning veterans who brought naval firefighting experience into civilian fire service. The adoption was gradual but steady. Fire departments that had resisted fog nozzles before the war found the evidence from naval combat compelling. Industrial firefighting, particularly in petrochemical facilities and refineries, embraced fog nozzle technology for superior performance against flammable liquid fires. Industrial fire brigades adopted both equipment and techniques developed by Burke and Lieutenant, recognizing that petroleum fires in industrial facilities presented similar challenges to those aboard ships. Fire service training evolved to incorporate lessons learned in naval combat. Fire academies built training props modeled on naval designs, creating realistic fire conditions where students experience heat, smoke, and conditions approaching actual emergencies. The emphasis shifted from classroom theory to hands-on experience, from lectures about firefighting to actually fighting fires under controlled conditions. The principles Burke championed became fundamental to fire science education globally. Fire engineering curricula taught the physics of heat absorption and steam generation, the advantages of maximizing water surface area, the tactical applications of fog patterns versus solid streams. What had been rejected as radical innovation in 1941 had become accepted wisdom by 1950, taught in fire academies worldwide as established doctrine. The story of Lieutenant Harold J. Burke and the fog nozzle illuminates broader truths about military innovation and institutional change. Several patterns emerged that remain relevant for modern military organizations facing technological and doctrinal challenges. First, transformative change often originates outside military institutions, from civilians who bring different perspectives and expertise. Burke succeeded not because he invented fog nozzles. They existed before his advocacy, but because he brought municipal firefighting experience into a military context and persisted despite institutional resistance. His civilian expertise provided insights that purely internal development would likely never have achieved. Second, overcoming institutional resistance requires demonstrated superiority under realistic conditions. Burke's verbal explanations and theoretical arguments convinced no one. His carefully controlled demonstration, showing objective measurements of fog nozzle performance, compared to traditional methods, provided evidence that could not be dismissed. The demonstration format, realistic fires, comparable conditions, quantified results, was critical to building credibility. Third, innovation requires internal champions with sufficient authority to mandate change. Burke's expertise and demonstrations were necessary, but not sufficient. Admiral Cochrane's support was essential to overcoming bureaucratic resistance and forcing fleet-wide implementation. The combination of external expertise and internal authority proved decisive. Fourth, effective implementation requires standardized training that proves new techniques can be taught systematically. Burke did not just train a few elite units. He created a scalable training program that produced hundreds of instructors who trained thousands of sailors to consistent standards. This standardization ensured that fog nozzle adoption translated into actual capability rather than just equipment distribution. Fifth, institutional resistance to innovation stems from multiple sources that must be addressed separately. Burke faced technical skepticism about whether fog nozzles worked, which he addressed through demonstration. He faced psychological resistance to equipment that looked inadequate, which he addressed by showing results rather than appearance. He faced bureaucratic resistance to admitting previous doctrine was flawed, which he addressed by framing change as modernization rather than correction. He faced cost concerns, which he addressed by documenting that equipment costs were trivial compared to ships saved. The lessons from Burke's experience remain relevant for modern military organizations. Technology continues advancing faster than doctrine, creating persistent gaps between what is possible and what is practiced. Civilians in specialized fields often possess expertise that military institutions lack. Yet military culture sometimes resists external input. Innovation requires overcoming the same patterns of resistance that Burke faced: technical skepticism, psychological discomfort, bureaucratic inertia, and cost concerns. Modern military services would benefit from systematic processes for identifying, evaluating, and implementing civilian innovations. Burke's fog nozzle should not have required Pearl Harbor's catastrophe to gain consideration. Earlier mechanisms for evaluating municipal firefighting developments might have prevented the losses that forced change. Cross-pollination between military and civilian sectors accelerates innovation in both directions. Burke brought civilian expertise into the military, transforming naval capabilities. Lehman brought military experience back to civilian firefighting, revolutionizing municipal fire service. The modern military should actively seek such exchanges, identifying civilian sectors with relevant expertise, and creating pathways for knowledge transfer. The story of Harold J. Burke stands as a reminder that history often overlooks its most important contributors. Burke never commanded a fleet or won a famous battle. His contribution was quieter, but no less significant. He gave the United States Navy tools and knowledge that saved thousands of lives and dozens of ships. He transformed how the Navy thought about fire and damage control, creating a culture of aggressive, confident firefighting that persists today. He proved that sometimes the most important innovations come from unexpected sources. From a New York City firefighter who understood that water droplets could be more powerful than torrents, that training could be more valuable than tradition, and that saving lives was more important than saving face. When USS Franklin steamed past the Statue of Liberty on April 28, 1945, she carried visible testimony to Burke's achievement. The carrier was a wreck, scorched and scarred, but afloat with hundreds of survivors aboard who would otherwise have perished. Burke was not present for her arrival. He remained with the fleet, training the next generation of damage control personnel, but his legacy sailed past the statue that day in the form of a ship that should have died but lived instead. In the end, that was monument enough for a man who never sought recognition beyond the simple satisfaction of knowing his work had made a difference. The ships he saved, the lives he preserved, the doctrine he transformed, these remain the true measures of Lieutenant Harold J. Burke's contribution to victory. His story deserves to be remembered alongside more famous innovations, not because he sought fame, but because understanding how fog nozzles came to save hundreds of ships illuminates how determined individuals can transform institutions, how civilian expertise enriches military capability, and how the smallest technical changes can sometimes yield the most profound strategic impacts. The fog nozzle revolution Burke initiated proved that innovation succeeds not through authority alone, but through persistence, demonstration, and the willingness to challenge assumptions even in institutions most resistant to change. His legacy endures in every ship that has been saved by effective damage control, in every sailor trained to fight fires confidently rather than fearfully, and in the fundamental principle that fire, like any enemy, can be defeated when men are armed with proper tools, effective training, and the courage to face flames knowing they've been prepared to prevail.